Hi, and welcome to TrainSignal and the continuation of the Advanced Features course. We're turning our attention to network load balancing in this section. A very useful tool to be able to help us support scalability, to be able to make our applications more robust, to be able to support a larger quantity of incoming requests, with support for some fault tolerance. We want to be able to handle the ability of something to break and allow our application to continue being accessible to its users. So consider for a moment the challenge of making any one piece of data available on a consistent basis. What do we do to make sure that we don't lose the ability to give to somebody the information that they want? Well, we'll put that data on a drive of some sort. Maybe it's a classic hard drive. Well, that hard drive is a single point of failure. What if that piece of hardware breaks? Well, okay, what we need now is two hard drives. So maybe we'll mirror the data and store a redundant copy on two hard drives. Which is fine, of course, unless those drives are both connected to the same drive controller on the motherboard of that computer. In which case, what happens if that piece of hardware goes out? Well, now we lose access to both drives. Okay, so we need disk duplexing. We need two drives attached to two different drive controllers connected to the one motherboard. Well, now that's a problem. I can't put more than one motherboard in the same computer. What do I need? Well, now I need multiple computers. I need redundant copies of the same data on multiple computers, so that if one computer goes down, another computer is there to be able to take its place. NLB, Network Load Balancing, is one of a couple of features of the operating system designed to provide that kind of multiple server reliability functionality. NLB specifically attempts to do what's called load balancing, to be able to receive a load, to receive a request for data, or indeed lots of requests for data from large numbers of requesters, and be able to spread that incoming traffic amongst some number of servers that are all able to simultaneously respond to requests from clients. It's a great idea. We'll see that NLB has the strategy of allowing traffic to come in to hit all the servers in our grouping of network load balanced servers, a collection called a cluster. The traffic hits all the servers in the cluster, and through the magic of NLB, each server uses an algorithm that determines whether that computer will be the one that responds to that particular request. So all this incoming traffic hits all these servers, and they automatically determine which one of them is going to be responsible for handling the request. It's a marvelous little bit of technology. So let's take a look at how to install one of these, and we'll work our way towards more sophisticated configuration. Like most features of the Windows Server family, we're going to install this from the Server Manager tool. And what I'm going to do is I'm going to put the actual NLB software itself, I'm going to cluster two servers and manage them from a third. So let me do two things. I'm going to install the client component on my Server 1, the Network Load Balancer Manager tool, and I'm going to put the NLB server-side software, the actual load balancing feature, on Server 2 and Server 3. Here's Server 2, on which I'm going to add the network load balancing feature. It is worth pointing out that NLB is not a role. Roles are the things that I might dedicate a whole server to. There's no point in having a server that has nothing on it but network load balancing. The whole point is to network load balance something. In this case, we're going to network load balance FTP servers by way of demonstration. So let me go add the network load balancing feature to Server 2. And while that's installing, I'll jump over and do the same on Server 3. So here we are on Server 3. We're going to add a feature here as well. So that gives us the server side of things. The next thing to do is to actually have some place to control this from. Now, depending upon how we configure the cluster, that certainly could be one of the servers that's being clustered, but I wanted to, for demonstration purposes, show you a way to be able to do that from outside of the servers that are being clustered themselves. So I'm going to jump over to Server 1 and install the client component over there. So here's Server 1. In this case, we're not adding the NLB feature itself, we're adding the configuration tool, the client component necessary to make that work. And in most of those cases, you'll see those in Server 2012 found underneath a category here called Remote Server Administration Tools. Now in this case, it's kind of a local administration of a sort, or at least it certainly could be, but in any event, we definitely do need the tool to do the administration of this feature. Note that Microsoft does break it down by feature administration and role administration tools. This is a feature, it needs a feature administration tool. there it is, Network Load Balancing Tools. So let me install that there, and then we'll be ready to actually see this start to take shape. Okay, now the client component has finished installing. Let me go take a look at the servers and see if they've also finished their work. Server 2 appears to be in good shape. And server 3 is all set. Alright, so we're ready to actually use the clustering software. We've got the clusterable components on servers 2 and 3. Server 1's where we're going to actually start the process of actually building a cluster. So what we're going to do over there on server 1 is begin the process of configuring a cluster of network load balanced hosts, network load balanced nodes, computers that are together being grouped together for a collection. The overall strategy is to create an illusion such that multiple physical computers look like just one server. The expectation for somebody connecting to some resources is they connect to the one place where the resource is stored and then get connected to it. And that seems logical enough. But in a lot of cases, of course, we know that that's a single point of failure. What if that one copy of whatever that is fails? Well, now we've got a problem. So our solution is to be able to create this pleasant illusion of a single server being created by the coordinated interaction of quite some number of servers. NLB in Server 2012 supports up to as many as 32 servers in a scaled out NLB cluster of this sort, if that helps to know. So that can be a really rather interesting thing to do. So we're going to configure a cluster IP address. We're going to give the cluster a name. We're going to give it an IP address. And that IP address is not going to map to any one particular computer in the organization, but it is going to be the identifier. It's going to be the IP address of the cluster as a collection. We're essentially creating a virtual computer out of thin air that's going to be able to respond to a great many more requests than any one individual server possibly could, with the benefit of knowing that if any one of those servers were to fail, the overall cluster continues providing resources to those who are requesting them. It's a neat trick. So we need to configure that clustered IP address. We need to identify which computers are going to be in the cluster. We need to set a priority order amongst those servers. That becomes important in a little bit. We need to choose an initial status for each host. When those computers reboot, do they start running the cluster? Do they start by hanging back and waiting to be told it's time to go? That sort of thing. Each computer also has, of course, its own dedicated IP address, the IP address with which it starts the process. Depending upon how the cluster is configured, that client may continue to be accessible via that original IP address, or it may not. We'll talk about some of the details of that a little further in. So I'm back on server 1. I want to be able to illustrate the NLB functionality, so we'll do that by building a network load balancing cluster. The starting point, of course, is to launch the NLB GUI, which is available here thanks to the install we did a little bit earlier. Having done that, I can right-click the NLB cluster tool and create a new cluster. The starting point is identifying one of the computers that will be part of the group. Once we've created the cluster using that first node, we'll then add in the others. So in this case, I've got two servers that are running as FTP servers. And to illustrate, let me launch my PowerShell window and do a quick FTP connection over to NYC-server 2. Server 2 is an FTP server. I've configured it for anonymous login, so I'm actually going to use the -A command line switch to say do an anonymous login. Don't bother prompting me for a password, that sort of thing. So that worked. How do I know? Because I set up a banner that says welcome to server 2. Looks good. If I quit there and try to connect to server 3, you'll see server 3 is connected. Yep, I'm connected to server 3. So that looks fine. FTP servers are what you'll commonly see lying behind a lot of your web server downloads. You're visiting a web page, you get to the place where the website invites you to download the new version of the demo of the software, that sort of thing. In a lot of cases, that web server is handing off control to an FTP server. The FTP server is what's going to be handing over the file that you're going to end up downloading. So, having more than one of them is a reasonable thing to do. If one fails, the other one's still running. We want to make sure that our clients visiting our website can continue to download the file. So, what do we do about that? Well, what we're going to do is make sure that when somebody tries to connect to that FTP server, that there's not just one FTP server there, that there's in fact two of them. Now we could simply just have two FTP servers and configure the web server to use one of them, and when the one FTP server fails, to manually reconfigure the website to point at the other one. That's something we could do, but we'll lose some business in the meantime because some customers will try to download the demo of our software and they won't be able to because it's not available. So probably what's going to happen is if we present to our boss the idea that says, hey boss, we've got two FTP servers we can just manually cut over whenever we want to, the boss is going to say, well, wait a minute, what if it's the middle of the night? What if one of those servers fails and we don't know until the next morning? What about all the customers overseas who aren't going to be able to download until morning our time? How can we make sure that we utilize those two FTP servers in such a way that if one of them is unavailable, the other one automatically takes over? Well, an NLB cluster is a good choice for that. So as I build my cluster here, my starting point is identifying the host and then choosing which of the network adapter cards on that computer is the one that's going to be my starting point. In this case, I'm going to choose Ethernet, the one that's using the 172.18 range of addresses. Having done that, I'll click Next. We can see basic host parameters as we begin getting our cluster online. We'll see that cluster members have a priority number. And in the case of certain kinds of traffic that hasn't been identified for where it's going to be sent to, the priority acts as kind of a fallback tiebreaker for which server is going to handle certain traffic for which the actual destination hasn't been specified. One is a perfectly logical choice here. We can see the built-in IP address of that computer, the .2 address. We get to specify what the default starting point is for this computer. Does it start in a stopped state? Does it start paused? Or does it in fact start up when I boot it up? In this case, I'm going to say that I want to start it. And I will, if I do through a reboot, I'll drop it into the suspended state to be able to recover from that in a somewhat more manual process. Next important question, an IP address for the cluster. This is the cluster IP address. What that means is that from the perspective of the network, the cluster is kind of its own computer. That's true in a networking sense. I'm able to go ping the IP address of the cluster and get a response. I'm able to target requests to the cluster's IP address and get a response from one of the computers in that cluster. Now, which one is a matter of discussion that we'll get into a little bit further in. But for the moment, first thing it's important to realize is that the cluster needs an IP4 or an IP6 IP address. I'm going to build an IP4 address. There we go. We're going to use my class C subnet mask. There we go. My cluster has a cluster IP. Needs a name. If you're clever, you'll go ahead and move over to your DNS server and build a DNS entry that describes this name and this IP address. That way people can get at it via name rather than number. Down at the bottom is a very important decision to make. Cluster operation mode. Cluster operation here determines how the system manages the relationship between the MAC addresses of the network adapter cards and the incoming IP address requests. The request is targeted at a normal computer with a single IP address attached to its single network adapter card. The way networking ordinarily works is that we engage the ARP protocol, Address Resolution Protocol. So we send an ARP request that says, hi, I see you have that IP address, but please tell me what's your MAC address? And the computer replies with a 48-bit MAC address, one of these things that we see up here. In unicast style operation of NLB, the system bends those rules quite some bit and instead tells each network adapter card of each member of the cluster, each cluster node, to hide its normal MAC address away and to instead use the MAC address of the cluster as its MAC address, which means that the only way to contact these computers is to use that one MAC address. The original addresses of those original computers aren't accessible anymore. There's no way to get to them. So you had to be careful in setting that up. If I tried to remotely administer the computers that are part of the cluster, connecting to a specific one, trying to use its old IP address, I won't get there because my old IP address in my ARP table is associated with the old MAC address. The old MAC address is something that the client is not going to respond to. The network adapter card is going to pretend that it never had that MAC address. A more logical choice for many environments, particularly if you're just experimenting with NLB for the first time, is a multicast configuration. Under the multicast configuration, We are going to leave all of the original IP addresses and MAC addresses as they are on each of the original cluster nodes. But in addition, each network adapter card is going to get an additional multicast IP address with a multicast MAC, and that will be the address that the cluster uses internally to be able to direct traffic at nodes for processing. This is the one that you're going to see me use for this demonstration. A third option, and a more sophisticated one, is called IGMP multicast. You can see that it's warning me as I set that up that there are important prerequisites to making that work. The prerequisites are in the hardware in your network. The challenge with multicast is that multiple computers all share the same MAC address, the same IP address. That can be a little bit confusing for switches if you've got your NLB cluster nodes connected through switch hardware. The switch doesn't necessarily know on which port your NLB hosts are located. So the default behavior is that the switch is going to do what's sometimes called port flooding. It's going to send these multicast messages out through every available port on the switch, hoping that through one of them, or more of them, one of them, is an NLB node waiting to catch that multicast message. That's less than optimal. And there is hardware out there that's designed to support that. There are switches that are designed to support IGMP multicast messages, where the switch is smart enough to learn the presence of the NLB hosts that are out there and manage traffic appropriately. So these multicast messages only go down the wires to the multicast capable NLB hosts. They don't go to all the other ports on your switch. So in this case, we're not going to bother to implement that. We don't have the hardware. We're just going to do a regular old multicast. We're using standard Ethernet type networking here, using an ordinary, in this case, virtual switch. We're using virtual machines. Next up is configuration of port rules. This is custom NLB configuration that we'll save for another lesson. But for the time being, it's worth pointing out that we get to set up rules about how the cluster is going to handle different kinds of incoming network traffic. And at the moment, what we can see is that incoming traffic for any port coming in on any IP address is going to be handled by throwing that traffic at a single node. Now, for demonstration purposes, I'm going to switch to no affinity. We will route it through our multiple hosts. We will not develop an affinity, a preference for any particular host. We've successfully built a cluster that includes server 2. We'll see that the status of our cluster node here is pending. It's waiting to finish getting everything nailed down. We'll see in a moment it'll shift into the converged state, which is to say that it has successfully done its work to get everything nailed up the way that it would like. And I'm going to be a little bit impatient here and go so far as to start adding my, oh, there it went. Adding an additional host, New York City Server 3, to my cluster. It'll again want to know which network interface to use. If I've got more than one, this server only has one NIC, so we'll use the one that it's got. Once again, familiar configuration options here. We've added our second cluster node to the cluster. That configuration is pending. We're in the process of getting these two NLB servers to talk with each other and agree about what happens next. And there we go. We have a converged configuration. Now, what does that mean? That means if I go back to my PowerShell window, I can still FTP to NYC-server2 with my -A switch and get in using server 2 by server 2's original name. But it also means that I can do this. I can FTP to 172.18.38.200. Now that's the cluster IP address. This is an IP address that was meaningless just a few moments ago. But I connected to it, and it says that I'm connected to FTP server 2. That's neat. Let me connect in again. There's server 2 again. Server 2 again. There's server 2. And there's server 3. Okay, so it didn't have a specific preference. We'll see that's because of the tweak that I made there, and we'll develop that idea more fully in another lesson as we look at customizing our NLB configuration. But for the time being, we've adequately illustrated that we can connect to a clustered IP address, an IP address for a computer that never did exist, but suddenly, as far as the network is concerned, now exists. Requests come in towards that IP address. Those requests are absorbed by these two servers, server 2 and server 3, and through the magic of network load balancing, they automatically know which one of the two is going to respond to those incoming FTP requests. This is a very powerful ability to scale up the availability of your application, to be able to increase the likelihood that if somebody tries to connect to some important component like an FTP server backing up a web server, that server will be reachable. I can add theoretically as many as 32 computers to a cluster of this sort, each time increasing the amount of available processing power over which I can distribute an incoming load of traffic. I hope using this will be able to help you improve the availability and efficiency of execution of your applications in your organization, and I look forward to teaching you more about NLB in another lesson.